Welcome back, everyone. In this video, I will be continuing the limit definition of the derivative section. Last video, what we did, where we stopped off, was really understanding what the derivative is telling us. In this video, we'll actually compute some derivatives and see it all come together. Now, fair warning, computing derivatives using the limit definition of the derivative, which is what we're doing, is not an easy task in most cases. But the things you'll learn in this section are really going to teach you also new ways to simplify that you never used before and new algebraic simplifications. All right, so let's go ahead and jump right into it. One thing I want to read here before we move on is we will practice calculating the derivative. And since it is the slope of the tangent line at that point, we can use it to find the equation of the tangent line. Could be very helpful for number one, because what we want to do here, number one, it says let g of x be equal to x squared minus 3x plus 7. Find g prime of a, so we want to do the derivative at x equals a, then use this to find the equation of the tangent line at 0, 7. Now, why is this so important? Well, if we want the equation of a line, we always need the slope, and the slope of the equation of a tangent line is the derivative. And we want the derivative at the x value indicated here, at x equals 0. So what we're going to do is we're going to figure out a formula for the derivative with a, and then we'll just plug in a equals 0, and that'll give us the slope. Now, a little sidebar here, what I want to go ahead and write down is anytime you find the equation of a tangent line, you will use point slope form, which is y minus y1 equals m times x minus x1. The reason you'll use this is that x1 and y1 are pretty much going to be given to you in the problem. And then the slope m is the derivative that you're figuring out. And once you have the slope, you plug them in and you're done. All right, so let's go ahead and do it. We've got g of x equals x squared minus 3x plus 7. Well, the definition of the derivative, we do the limit. I'm going to pick the one where h goes to 0. We have g of x here, so I'm going to do a g of x plus h minus g of x over h. And just as far as notation goes, I guess what I need to do real quickly is not use x here, but use a, because we want g prime of a. And that's what this is going to equal. All right, so let's go ahead and plug it in. We have the limit as h goes to 0. What does g of a plus h mean? That means everywhere in g of x we see x, replace it with a plus h. So we're going to have a plus h squared minus 3 times a plus h plus 7 minus, and when you subtract off g of a, because there's a lot of things here, use parentheses, make sure you use parentheses, you get a squared, because we're plugging in a for x, minus 3a plus 7. And let me fix that number on the limit and make very clear that it's 0. Okay, and this is all over h. Now, pretty much what you're going to happen as we go through is ultimately we want an h up here to cancel out, because we're going to get 0 over 0 if we plug in h as 0. And we know from previous sections that when we get 0 over 0, canceling is what makes the 0 over 0 go away. So that's what we're looking for. And the only way to get to that point is just to simplify as we go. We got the limit as h goes to 0, and we want to simplify this numerator. Well, anytime we multiply something or square something, it's multiplying it by itself. So this is going to be a plus h times a plus h. And then we got minus. You can directly distribute the 3 in through because there's no exponent on the outside. We got minus 3a minus 3h, and then plus 7. And then back here, you want to distribute the minus sign through as well. So that's going to be minus a squared plus 3a minus 7. But this entire thing is over h. Now, one thing you can really do to help yourself is simplify as you go. Don't try to wait till the end. And usually when you do limit definitions of derivatives, they do simplify as you go. All right, so what I want to point out here is the 7 will cancel out with the minus 7. But also the minus 3a here cancels out with the 3a there. So we do have quite a bit of simplification already. Now what do we do? Well, the next step really, we don't have much to do yet. We need to square this out. We need to multiply this out by foiling. So a times a would be a squared plus a times h is exactly that, plus the insides h times a, plus the last h times h is h squared. Now after this, what we're left with, we have a minus 3h and a minus a squared. And then this is all over h. Now once again, at every step, when you do the limit definition of a derivative like this, see if you can simplify. And we do have more cancellation because the a squared cancels out with the minus a squared there. What are we left with? We got the limit as h goes to 0. On top, we have a times h and h times a. Those are the same thing because order of multiplication doesn't matter. That means we have two of them, 2ah plus h squared minus 3h. And that's all over h. Now, what do we want to do from here? We still haven't canceled anything from the top and bottom. We've canceled out a lot just on the top, but nothing from the top and bottom. If you plug in h as 0, you're still going to get 0 over 0. Well, at this point, there's not really anything obvious to do. There's nothing to multiply out. There's nothing to distribute. But we do have an h in common everywhere in the top. And if we factor that out, that'll help us. So let's factor an h out. We have the limit as h goes to 0. The bottom is just h. Now, if we factor an h out of the top, then our first term, we got 2h. Plus the second term, we took one of the two h's out. We still have one of them. And then in the last term, we have a minus 3 because we took that h out. Whoops. And I only want minus 3. All right, now what you should notice is what we really wanted to happen. At this spot, we can cancel the h because it's factored out. We can cancel it with the h in the bottom, and we're left with the limit as h goes to 0 of 2a plus h minus 3. Now, we don't even have a fraction in here, but once we get that cancellation, you want to go ahead and do your limit, which means plug in the 0, and we get 2a minus 3. That is our g prime of a. Now, if you're just unsure of when you're done finding the derivative like this, the derivative is just the limit. So once you can plug in 0 and simplify it, that's your derivative. And we have 2a minus 3. Now, what do we want? Well, we've got the derivative formula. We really want the derivative at x equals 0 or a equals 0 since we have a here. Let's go ahead and plug it in. G prime of 0, which is going to be the slope of our line here, m. We plug in 0 for a, we get 2 times 0 minus 3, which is negative 3. Now, one thing that's really a hard habit to break, you don't have to simplify once you plug in here. When you get the equation of a tangent line, it's almost always best to just leave it in its point slope form with everything plugged in. But what I mean by that is we have y minus y1, which is 7, equals m, which is negative 3, times x minus x1. x1 is 0. Now, normally I would simplify x minus 0 to just be x because it is. But when it's read like this, you can easily see what the slope is, negative 3, but also what point was plugged in, 0 and 7. It just makes it a lot easier to deal with. Now, if you want to simplify, you can go all the way down and get to y equals. And we would have y equals negative 3x plus 7 if you went through the steps. But it's up to you if you want to solve for y. What I really want to do here is go ahead and solve, or not solve necessarily, but I want to graph the original function. I want to graph the tangent line, and I want you to be able to see exactly what the tangent line is. We already saw it before, but this should really help confirm what the tangent line looks like. We have g of x, which I'm going to use y for, equals x raised to the 2 power minus 3x plus 7. Right? I'm zoomed in super close, so let me go ahead and zoom out. I wanted to make sure we're already centered where we're going to be. We want to find the tangent line at this point, 0, 7. Let's go ahead and now type in the equation of our tangent line, which is y equals, or actually, let me go ahead and type in the original one. Y minus 7 equals negative 3, x minus 0. Now, you may have been inclined to think, I need y equals in Desmos, but you don't. It knows how to graph when it's not y equals as well. But what I wanted to do is point out that at this point that we found the tangent line, look at what the graph exactly looks like. The parabola, which is the original, the green one, is the graph we're trying to find the tangent line of at this point, and our tangent line does what? It pretty much just does exactly what we said before. It looks like it's parallel, it's just kind of touching the graph at this point. And if you zoom in farther and farther, you'll pretty much see that the purple overlaps the green. And that's one property about tangent lines that's pretty common, is that the tangent line, when you're graphed at a point, pretty much overlaps really close the actual graph. And that's useful. That'll be very useful going forward. But I wanted you to actually get another visualization of a problem that we did together, and you can see the tangent line. All right, now for the next one, I'll go ahead and move that out of the way. We want to compute y prime if y equals x to the 1/3. Now, whenever you have fractional exponents or radicals, this is one of the examples where it could be easier to use the other limit definition of the derivative, the one with x and a, the one without h. So let's go ahead and just do the other one. Let's do the limit as x goes to a. And remember, the formula for that one was f of x minus f of a over x minus a. And f of x is just x to the 1/3. We're using y here, but you can think about it as f of x. The limit as x goes to a. And f of x is exactly that. It's already just x to the 1/3. F of a means take our equation here and plug in a for x. We get a to the 1/3 over x minus a. Right, now here comes the much more challenging part. Because we have a fractional exponent like this, it's really a radical. I'm going to do a little bit on the side here, because when you have something to the 1/3, when you change it to radical form, the exponent, the numerator, is the exponent inside the radical, and the denominator is the exponent or the number on the radical. So this is really the cube root of x minus the cube root of a. Now, how do you think we simplify this? Because we eventually need something to cancel. Well, when we had square roots before with limits, we did the rationalization trick, and that allowed us to cancel. The idea is we still want to rationalize, but when you have a cube root or any root that's not a square root, it's a little more complicated. What you have to do is figure out what to multiply this by to get a whole bunch of stuff to cancel out. And you may not be familiar with this formula, but it's going to use the difference of cubes. If you don't have this memorized, that's okay. It's just where this is going to come from. The reason we rationalize the way we do is we actually are using the difference of squares, because the squared is the inverse of the square root. So the reason we're using the difference of cubes here, cubing the inverse is the cube root. Now the formula for the difference of cubes is x cubed minus a cubed. I'm going to use the same letters we have here, equals x minus a times x squared plus ax plus a squared. Now what you can do is go ahead and FOIL. You can't really FOIL because it's three things, but distribute this side out and you'll see that you get this. Now, how are we going to make use of this? Well, we want to see an x to the 1/3 minus a to the 1/3 in this formula. The way to do it is think about, instead of having x minus a here, what if we add that x to the 1/3 minus a to the 1/3? Well, if we think about doing the cube root of every little portion here, every single part, so we would have x to the 2/3 plus a to the 1/3 x to the 1/3 plus a to the 2/3. What is the cube root of each part of this? Well, this would be x minus a. Why is this going to be so useful? Well, what this is telling us is if we multiply our x to the 1/3 minus a to the 1/3 by this, it'll just be x minus a. So I know that sounds confusing. You have to know this difference of cube formula, but this is really where it comes from. So if in theory, you wanted to do x to the 1/4, you would find the difference of fourth powers formula, whatever they're called. And then fifth, same idea. And I'll write a general formula for you afterwards if you wanted to use it. Right? But it's pretty much necessary to use here. What I'm going to do is exactly what I described above or below. I want to take this x to the 1/3 times a to the 1/3. And I'm doing some sort of rationalizing, but the thing I'm multiplying by is x to the 2/3 plus a to the 1/3 times x to the 1/3 plus a to the 2/3. And what I do to the top, I must do to the bottom. Okay. All right. So right here, it looks pretty messy, but a couple things you want to remember. When we rationalized before, what did we say to do at the part where you're not trying to get stuff to cancel out? Leave it factored. So the denominator, as messy as it is now, I'm going to leave it like this. X minus a times this messy part. X to the 2/3 plus a to the 1/3, x to the 1/3 plus a to the 2/3. All right, what about the numerator? Well, when we multiply the x to the 1/3 minus a to the 1/3 times this, you can go through and check it, but that's what we established below. This is going to become just x minus a. All right, once again, I encourage you to multiply this out and check it, but all we did was we used our difference of cubes formula, and we just did the cube root at every part, or 1/3 power if it helps to think about it like that. All right, now why is this so useful? Well, you have an x minus a on the bottom factored out and x minus a on the top. That's something you can cancel. It's no different than if this was just x, because if it was just x on the bottom and top, we would cancel out. X minus a is just a different expression, but they're matching, so we can cancel. Don't forget that there's really a 1 there on the top. And we have the limit as x goes to a of 1 over x to the 2/3 plus a to the 1/3 times x to the 1/3 plus a to the 2/3. All right, now that we got the canceling happen, remember that's really after that point of cancellation, that's when the 0 over 0 should not happen. And we can plug in now what it says to. We want to plug in x equals a. So when we do that, we plug in a, we get a to the 2/3, 1 over a to the 2/3 plus a to the 1/3 times a to the 1/3 plus a to the 2/3. Now a to the 1/3 times a to the 1/3, when we're multiplying, we add the exponent. So this is really a to the 2/3 as well. And what you'll notice is we have a to the 2/3 plus a to the 2/3 plus a to the 2/3. That's 3a to the 2/3. All right, now this would be y prime at a. If you wanted just y prime in general, usually we use x. So y prime, all you would do is just take your formula here and replace it back with x, and you get 1 over 3 x to the 2/3. But if you want y prime of a, leave it like this as well. Either one's fine. All right, now we weren't asked to do anything else with it. All right, so what I'm going to do as a resource, and I'll have it on the bottom of this lecture, is I'll write the general formula for a difference of powers. So if you have x to the n minus a to the n, really probably never going to go past 4, because beyond that it's just nothing anyone memorizes. In fact, really people don't memorize past 3, but I'll go ahead and give you 4 at the end of the lecture. I'll just add it in as the notes. All right, now I think that's a good place to stop. In the next video, I will pick up where we left off doing this problem.